I have never been wired up that much before. So thank you for the invitation to be here. It's a wonderful place and a wonderful meeting. So I have to start with a small disclaimer, in the sense that I am a mathematician and I work in algebraic combinatorics. So my point of view, maybe on the same models that you study, is probably quite different, and also the terminology I will use will also be different. So I hope that you will recognize, probably better than I do, the models and relate to them. But I will talk mainly about Lozenge tilings. Lozenge tilings, as you know, correspond to the non-intersecting lattice paths, dimer models on the hexagonal grid, 5-vertex model, and so on. So I will, however, use the perspective of the tilings to describe what I want to say. And the other thing is that the methods I will use are from algebraic combinatorics, and maybe you don't really know what this is, or maybe you've seen it, but you didn't know it was called like this. So I will actually start by explaining a little bit about the background of the tools that I will use, and then explain the models. Okay, so algebraic combinatorics. What is combinatorics in general? People use these words all the time, meaning that they are probably counting something discrete, some discrete structure that satisfies some kind of restrictions that are easy to describe with a set of integer parameters and so on. So all of this, of course, is combinatorics. Where is the structure coming from here? So one can start with simple notions like permutations, as you all know what this is, and then go in the sense of algebraic combinatorics. Everything that we do is somehow motivated from algebra and representation theory and algebraic geometry. So this is where the discrete objects come from, and these are the notions that we use. So using these permutations, we start with, they form a group under the composition of permutations. This is the symmetric group. And then one can study the representation theory of this symmetric group, and so you use representations all the time, although we probably prefer the algebras. But the symmetric group, the irreducible representations are indexed by the integer partitions of n. Integer partitions, hope you all know, there's just a sequence of non-negative, weakly decreasing non-negative integers which sum up to n. And they have a very nice graphical representation in terms of Young diagram, and this is actually very important notion, so that these sequences of integers can be described, can be visualized with a Young diagram. The number of boxes on each line corresponds to the integer here. So line 1 is lambda 1, line 2 is lambda 2, and so on. And the next step, when you study the representation theory of the symmetric group, is the basis for the irreducible representation. So as I said, that the irreducible representations are indexed by these integer partitions, and there is a way to construct a correspondence between the basis for these irreducible representations for each lambda and what is called standard Young tableau. So this is another important notion that will come into the study of tilings and other models. And standard Young tableau are just assignments of the integers from 1 up to n in the boxes of this Young diagram, so that each integer appears exactly once, and they're increasing along rows and down columns. And these objects themselves have a lot of interesting properties and are subjects of many studies. And then, so this is the finite, in the finite world. If we go to there is some notion of duality, Schur duality, where we can also study the general linear group with similar objects. And the reducible representations of the general linear group are also indexed by integer partitions. This time, the number of non-zero parts is what is limiting us. It's the size of the general linear group here. And again, we have some combinatorics, algebraic combinatorics here in the study of symmetric functions. Where do the symmetric functions come from? For example, they come from the characters of the irreducible the Weyl modules for the general linear group. And the character, if we have a matrix with eigenvalues x1 up to xn, then the character of the corresponding representation is this Schur function as lambda, evaluated at x1 up to xn. And one can define them, so forget about all the representation theory, one can define them with this ratio of determinants, Weyl's determinantal formula, or from the point of view of combinatorics, and this is what we will also use, we can define them with the notion of generating function. So we go over all semi-standard tableau of shape lambda. So what's a semi-standard tableau? Again, we have the partition, the Young diagram of the partition lambda, and we assign the numbers from 1 up to big N here, except that this time we can allow repetitions, and the numbers would be weakly increasing along rows, but strictly increasing down columns. And so here, if we use just the letters, the numbers from 1 up to 3, and we have this shape, these are all the possible semi-standard Young tableau we get. And for each tableau, we assign the corresponding monomial in the sense that for every number I, we assign xi to the number of times that this value appears here in the Young tableau. And it turns out that this is equal to this, which is already somehow non-trivial and not obvious to see. Okay, so why did I start with this? So these Schur functions will be a tool for studying lattice models, as you will see in a moment. And in particular, I will focus at least for the first half of the talk on this notion of normalized Schur function. So we take this Schur function as lambda, and we have the variables. We use formal variables x1 up to xk. K is some fixed number. For the rest, we plug in ones. And we normalize by the value of this Schur function at 1. So this is again it is in a sense a moment generating function or a Laplace transform that you will see in a moment. And the interesting thing is that these types of functions show up in the study of observables for many of the lattice models. So here I have drawn some of them, the 6-vertex model and alternating sign matrices, that you know, the dense loop model and so on. So in these cases, the connection is not very direct, and we can only get a little information out of these functions, but of course these models are much harder in sense. But in the case of Lozenge tilings, there is a very nice correspondence and combinatorics that is relating this to this model here. So I will now go to Lozenge tilings. What are the Lozenge tilings? We have a triangular grid. We draw a domain in the grid, so this blue region here, and we tile it with the 3 types of rhombi. So there are 3 ways you can connect to adjacent triangles from the grid. And of course, a tiling means that you don't have any overlaps and that you don't have any holes in the domain. And so this is one particular tiling or a particular configuration of the model. And of course, you know that this the Lozenge tilings of the triangular grid, if you take the dual of this triangular lattice, then you get a dimer model. So the lozenges correspond to dimers on, in this case, it's going to be the hexagonal lattice, and again you have some region, the region in the hexagonal lattice, so these are the dimer columns. And you also probably would relate more to a picture like this, but actually I realized that I drew the dual, the dual of what you are probably used to, but there is a way to see these Lozenge tilings as non-intersecting lattice paths. Semi-standard Young tableau also correspond to non-intersecting lattice paths, and non-intersecting lattice paths correspond to the 5-vertex model. So what are the lattice paths? First of all, one can, so this is, yeah, so I did draw the dual of what people normally do, is what people normally do, they assign particles to the white rhombi along the line, and then these particles would be jumping. So line by line would be some kind of evolution process where the particles are jumping ahead. And in this case, one can draw the dual picture of what I just said, which is what is here, and then the lattice paths correspond to the movements of the dots, the red dots here, and the 5 vertices in the 5-vertex model would correspond to the 5 ways that a lattice path can move through one of these boxes here. So because you don't allow intersection, then you're missing the cross. So in the to get the 6-vertex model, so that's only the only 5 vertices are allowed. Okay, so now what are questions related to Lozenge tilings from a probabilistic and even so physics point of view? One can study the limit behavior of Lozenge tilings. So what do we mean? We take a domain in the plane and we let the grid size, the mesh size go to 0, or we have a domain which is growing in a regular fashion that we can describe, and then we shrink things back up, or we zoom in a region and we ask, how does it look? If we take, let's say, a uniformly random Lozenge tiling of this region, how is it going to look in this domain? What's going to be the probability law for various observables and so on? And so this has been, this topic started developing in the 19th, where people first observed that there is a frozen region. So if we take Lozenge tilings of the hexagon, and the Lozenge tilings, of course, have this three-dimensional visualization. So it's the 3 types of lozenges are the 3 sides of the cube. Then with probability 1, we are going to see that we have only lozenges of one type beyond a curve. Actually, and depending on the domain, this is going to be an algebraic curve. In this case, it's an ellipse for the hexagon. And there were many results, of course, listed here. Then one can start asking law of large numbers. So as you can see, this looks like a surface. And there is a correspondence with the height function for the model with the actual heights of these boxes in the picture. So one can ask what is a typical surface, or is there actually concentration happening? So are most Lozenge tilings close to some particular deterministic surface? It turns out yes. and so on. So one can also zoom in near the boundary and ask what is the probability law for the if the random variables are these the heights of the horizontal lozenges here near the boundary, what's their joint distribution and what's the probability law? And it turns out there that we have the same law as the one for the eigenvalues of random matrices from the Gaussian Unitarian sample. And so how do we prove many of these properties? I will show how one can use these Schur functions and algebraic combinatorics to do this. But before I go there, I want to extend the models in a maybe unusual way and impose a global symmetry. So usually we have, so far it's unrestricted Lozenge tilings. As long as we fix the domain, then every tiling is equally, so the uniform distribution would give you equal probability for every tiling, but one can also do another version where you impose some global symmetry of the tiling. So for example, we can only pick uniformly at random from tilings which are vertically symmetrical about this axis. So now it's not really a local definition for the weights, but we have a global condition. And one can also ask for centrally symmetric Lozenge tiling. So we have this hexagon here. We take the center and we ask for Lozenge tilings which are symmetric about the center. So if we have a lozenge here, horizontal lozenge here, then the corresponding line there should be the same one on the other end. So of course, the symmetry should hold for the entire domain as well in order to make this possible. And one can ask the same type of questions. What are the fluctuations near the boundary? Is there a limit surface or a law of large numbers for this entire configuration? What about central limit theorem? So if you zoom in, how do things behave? And so on. And so near the boundary, as I already mentioned, that we have this Gaussian unitary ensemble distribution for the eigenvalues. How does the correspondence go? If we have a flat boundary here, let's consider the horizontal lozenges on the vertical lines when we start moving one by one from the flat from the vertical line on this end. And then this number x corresponds to the height of this lozenge on the picture. The height. So it really doesn't matter for this because of the scaling, but one can think of the height as counting from this this line here. So how far are these numbers going? And because of the boundary condition and the combinatorics, then these heights, as you can see from the picture, they satisfy this interlacing condition. So x111 is going to be less than the bigger number on the second line and bigger than the second number on the second line, and so on and so forth. And all these numbers, so what is their joint probability distribution? It turns out that as we rescale accordingly and let the domain size m go to infinity, the joint distribution converges to what's called the GUE corners process. So these are which I will define in a moment. And so what is the GUE corners process? We take matrix from the Gaussian unitary ensemble, and we consider all the submatrices, the principal submatrices which are contiguous, which can comprise of contiguous rows and columns starting from the top to some place here. And it's a theorem in linear algebra, of course, that they are going to have real eigenvalues, and if you arrange their eigenvalues in increasing order, then the eigenvalues from the matrix, the big matrix, the one inside, and so on and so forth, they will interlace. So they will satisfy the same inequalities of this triangle that I showed earlier. And so this collection of so-produced random variables is what's called the Gaussian unitary ensemble minor, so corners process. And I will denote it by GUE K. So now we have this generalization of Gaussian random variables in some sense. And in order to describe what the behavior for the Lozenge tilings is, I need to make a setup for the domain and parameterize it in a way that we can extract the information. So how are we going to parameterize the domain? And this already implies that we are imposing some boundary conditions that are not as general as one would like, but so far there hasn't been. In general, it is very hard to study this tiling. So we start with the domain will have three straight lines on this. So for these borders, and then on the right end, on the vertical right end, we are going to impose the positions for the lozenges on this line. So we start counting 1, 2, 3, 4, 5. So in this case, on the fifth line, we are going to say where the horizontal lozenges will be, and their positions will be some strict partition. So in this case, when we will be denoted by lambda. So lambda is again some integer partition. If you add the numbers from 0 up to n minus 1 to lambda, then you actually get a strict partition and corresponds exactly to the heights as you see them on the picture. And yes, so the combinatorics and the restrictions here imply immediately that we are going to have exactly n lozenges, horizontal lozenges on the nth vertical line. And now the domain is going to be given by this lambda. And if you want to recover the usual hexagon, which is the first domain that people studied and it's the best studied one so far, the way to recover it with this type of parameterization is by saying that lambda is going to be a rectangle. So just C equal numbers and then all zeros, and as you can see from the picture, this tells us that this region here is all flat and this region here is all flat, and the rest is just a hexagon that we are free to tile whichever way we want. So this lambda is going to parameterize our domain, and now one can state the result. So now that we have some parameterization, we can say exactly depending on how this lambda changes, what happens with, let's say in this particular case, near the behavior near the flat left boundary. And so this is like a meta theorem with all sorts of cases inside. So we have these vectors of positions of horizontal lozenges on the various vertical lines. So this here is the third line, and we can take them all together from 1 up to k. As I said earlier, these are going to be interlacing arrays of numbers. And now we subtract a mu n, which is a mean that will depend on the boundary conditions, and when we normalize proportional to square root of n. So now this entire collection, so this triangle of numbers for all the vertical lines converges to this Gaussian unitary ensemble corners process, the eigenvalues of the random matrices as I described earlier. And so what are the values of mu and sigma, and for what kind of setting? So this holds for, originally was proven for the tilings of the hexagon. Then we show that this holds as long as we have some nice behavior for this lambda, which is parameterizing the other end of the domain, if it's converging to some kind of limit shape, then these numbers are the sort of coming immediately from the limit shape, the mu and sigma, and we have this law as well. And now this also holds for the symmetric, vertically symmetric Lozenge tiling. So we have two parameters, so we have just n and how we rescale the hexagon. And again, one can get the numbers mu and sigma from these parameters. And for the centrally symmetric Lozenge tilings that I described earlier, where again you have this global symmetry, but again you can zoom in near the boundary and you have the same type of behavior with whatever parameters one gets from this computation. And the next thing one can prove using the same methods that I will show in a moment is that the so-called the law of large numbers for this model, or in other words, that there is a limit shape for the three-dimensional picture here that we are drawing. One can introduce the height function, rescale everything by n, and then all the Lozenge tilings are this height function converges uniformly in probability to a deterministic surface in R3, and this is what's the limit surface. So one can prove this for various depending on the domain. So again, originally it was proven for hexagon, then any polygonal domain. Then one can do this for nice family lambda of, again, this type of trapezoidal domain, and then lambda parameterizing the right border. And then one can also do it with this global symmetry that we are imposing, so vertically symmetric and centrally symmetric. I don't have a picture, but so this is how a big uniformly random tiling looks like, and this is about already as close to this limit surface as it gets. So how do we prove this? With these Schur functions and algebraic combinatorics, as I just mentioned. So let's see what the setup is here, and that's one of the reasons that I was drawing the particles in the 5-vertex model interpretation. Like this is the following picture. So here is our domain and our tiling. On the end, and we draw these vertical lines, 1, 2, 3, and so on. The end one is our lambda, which is giving us the border of the domain. So lambda 1, lambda 2, and lambda n. So these are the heights of these lozenges, and each of this sequence of numbers, so these are all the heights, yes? Yes. Yes, that's correct. But these are different regimes now that so I will not. So yeah, so it depends on how you take the scaling, what is changing, and so on and so on. So there is also Tracy Widom distribution here, which I'm not proving though. These methods will not, at the moment at least, do not give that. Okay, so is it okay? So yeah, so the scaling that we are using and the convergence that we are proving is different from what you're saying. So I hope that one is clear. So in this particular setting here, we have lambda n is fixed. And n is going to grow, but lambda n is growing in some regular fashion with n. So there's some deterministic way. And if lambda, this big partition is growing, so then the question is what happens with the little ones in the other end. So how does the model work here? So we have lambda. So these positions are an integer partition which we can draw as a Young diagram in the plane. And then we can draw all the next one, and so on. So we have all these nested Young diagrams. This one, the blue one, so we have height 3 and is only 1, so it will just give you a row of three boxes. So we have this Young diagram, then we have the next one, the red one, then we have the yellow one, and so on. And now if we draw them on top of each other and we fill the space between two consecutive ones, so between the ith and the I plus 1 with the number I plus 1, we actually recover a semi-standard Young tableau by the definition I just used earlier. What's the semi-standard Young tableau? We need to have weakly increasing numbers along rows and strictly increasing down columns. And we have the large partition lambda n is the big tableau where we live in. And now, if we want to look at the possible configurations we have here, how are we going to do this? So the probability that we see a particular sequence of integers on a given line k is what? So we need to have the first k numbers will have to give a semi-standard tableau of shape equal to nu. So this nu here. And then the probability that we will see this in this configuration is equal to the number of semi-standard tableau of shape nu and k entries in here, and then the number of skew semi-standard Young tableau of the remaining skew shape. So basically the region between lambda and nu. And number of semi-standard Young tableau with entries from 1 up to k is just the evaluation of the Schur function at 1 up to and at k once. So one can write the probability for seeing something on the vertical line, and this ratio of Schur function. And then one can form something that we called Schur Generating Function, or generally another version of a moment generating function. We have some formal set of variables y1 up to yk. Then this xk is random variable, so the random vector, the positions here. Then it is some kind of a partition, and then we take the expectation of the Schur function corresponding to this partition, to this random partition, evaluated at this formal variables y1 up to yk, and normalized. And this, by the combinatorics of this skew Schur function, branching rule, and so on, it turns out that if we have lambda fixed and we do this expectation over all possible Lozenge tilings, and we look at this random variable for the values of for the heights on vertical line k, then this is exactly this normalized Schur function that I introduced earlier. And now the idea is that one can study the asymptotic behavior of this thing here, and of course extract the behavior of the underlying random variable xk And so how does this work? So here we have this Schur generating function or moment generating function. And so as I said earlier, so when we have parameterized our domain by lambda, this is just the ratio, this normalized Schur function corresponding to lambda. But if we have the symmetric tilings, then we have other expressions, but they are closed form expressions. So there are some kind of ratio of Schur functions or products of normalized Schur functions or normalized symplectic group characters, which are similar to the Schur functions. And then one should compute the same type of moment generating function for the GUE distribution, and turns out it is this, and it's not so hard to prove in many ways. I can do this directly as well, because we know a lot about the joint distributions for the eigenvalues. And this is for the GUE, this is for the tiling. We have this, and now we need to take lambda to go to infinity in some regular fashion and see how, if we rescale these variables properly, whether we see some convergence, and yes, we do. So here is the rescaling that we need to take. This is sort of there we subtract the mean for the positions of these lozenges, and we get, using some analysis on these normalized Schur functions, we get this expectation, and then we can get the convergence of random variables as we wanted. So this under this normalization. Okay. So this is for the Gaussian unitary ensemble random matrices. For the limit surface, one can also use this Schur generating function. So I will go faster here, because these are a lot more technical details of how this works. But basically, one can use even weaker limits for this normalized Schur function. Just the largest terms and no rescaling. One can extract actually the limit surface as basically a deterministic measure for every horizontal line that you draw, and one can extract, in principle, the limit surface from a computation like this. So depending on the convergence of the Schur function, and again, so one needs some analysis of this normalized Schur functions to get the actual limit from this thing. So here is what you get. Of course, it's not anything. It's not your friend. So it's not. The limit surface is not something nice that you can easily compute, and it's always given by some implicit form, and in this particular case it's given by the moments of the measure, of the deterministic measure, which corresponds to this limit surface. And this is for the symmetric, the two types of symmetric cases, though one sees immediately that the symmetric limit surface is the same as the one for the uniform tilings of this symmetric domain, because this global symmetry is actually satisfied by both the limit case of the uniform tilings and the ones where we already impose it in the probability. And just to say what was under the hood, so when we did this analysis in order to do the convergence, one needs to do asymptotics of these normalized Schur functions. That's not something that comes for free. And the way we did this was with various integrals, steepest descent analysis, and so on. So here are the types of formulas that go behind. Later one could There are other ways also to do asymptotics of these Schur functions, but nothing is particularly straightforward. And do I have a little bit? Okay. All right. So I wanted to say to show you a different model and a different way of using Schur function and algebraic combinatorics. So this is in some sense completely disjoint from what I talked about before, except again we have Lozenge. So we have again a domain, we have Lozenge tilings. This time the weight for each horizontal lozenge is going to depend on its position. Okay, so the weight, the lozenge tiling, the lozenge at position ij. So here I introduce this type of coordinates. This is so the way to think about these coordinates is that we have this three-dimensional picture for the lozenges as stacks of boxes. We draw them as we do our usual projection to draw them on the pages we do here, and then we impose on top of this drawing we impose a grid, which is the 120 degrees angle lines here. So. And there are y and j coordinates. So I here and j here. So these are x's and these are y's. So if we have a horizontal lozenge like this one, which is at position ij according to this coordinate system here, then we assign it a weight x2. So it's line 2 here minus y3. It's line 3 on the other direction. And then the total weight of the lozenge is going to be the total weight of the lozenge tiling is going to be proportional to this to the product of all these weights for the horizontal tiling. So one can horizontal tiles, or one can think of that the other two types of tiles just have weight 1, and we just take product of all the weights for the given configuration. So in this particular tiling, this is gonna be its weight. Okay, so now these x and y's, of course, are some formal variables and probably doesn't have meaning always, but one can substitute actual values for x and y and get something meaningful. So in particular, here is a simulation where X and Y's are actually distances from the end of our domain on this flat projection. So one can substitute xi to be n minus I and yj to be j minus n, and then we get that the weight at position ij is this 2n minus I plus j, or in other words, this is the weight here is proportional to the distance from the box of this lozenge tiling. And here one can do weight 1. Weight 1, of course, you get by saying y is equal to 0 and x is equal to 1 always. One does recover the original model. And so here is a simulation, under these weights, and here is a simulation under these weights, and you can see that there is some kind of elongation happening. So there is something else. And now one can ask for this model, one can ask all the previous questions that I asked, and we are nowhere near to solving them because this doesn't fit so nicely with the combinatorics. But let me tell you where this came from and what kind of formulas we have. So okay, so here is our model. Here is our lozenge tiling. It corresponds to what's called a plane partition in combinatorics. boxes that are stacking on top of each other. And these numbers here, they are weakly decreasing along rows and columns, and they correspond to the heights of the horizontal lozenges, on the blue lozenges on top of, starting from the base of this three-dimensional configuration. And again, so here is the weight depends on the position of the lozenge, and it's going to be x minus y5 in this case. And so what is the partition function for this? So we go over all tilings from all possible tilings of this domain. So d is going to be the height here, and mu is going to be the base for this tiling. So we have something that is part of a hexagon, but the bottom is cut out, given by mu. And if we go over all tilings under these weights, it turns out that we have a determinantal formula, and you might say that, oh, but this is non-intersecting lattice path integrable. We already have determinantal formula. Well, this is a different determinant. And a lot nicer probably than what you would get by just doing non-intersecting lattice path. This one, yes, so. Yeah, no. And so this is the determinant that one gets for this picture. So it comprises of there are zeros in this, and so under this diagonal, and the other entries are these products of the variables. And of course, one studies this when you plug in the variables in certain ways. So one recovers using this formula. If you plug in, for example, xi to be q to the I and y to be 0, or xi to be q to the I, y to be q to the j, or something like that, then you can recover these formulas from the literature earlier on, derived by Krathenthaler, Richard Stanley, and so on. So for the determinantal formula for the plane partitions, given shape and height d, or this picture that I showed earlier, where we have q to the volume measure this time. So q to the volume, just q to the number of boxes that we see in this picture. And again, we have this type of determinant. And one can also, because we know this, we know the partition function for all possible bases mu that we take our stacks of boxes, we can also say, consider lozenge tilings under these weights xi minus yj, and consider the probability of seeing a line like this cutting at a certain place, or this is what we call a path, and the path is going to be a ratio of two determinants, and this is the entire partition function for the hexagon. Again, is certain type of determinant. So one can calculate many things using these determinants. The only thing so far it is hard to get is what is the probability of seeing particular horizontal lozenges at certain places, which would help us analyze the entire thing probabilistically. But where did this come from? So a small digression where these formulas came from. In some sense, it came from algebraic geometry, but so here is the story was about counting the standard Young tableau that I was showing in the beginning. And if you might have heard that the number of standard Young tableau, or the dimension of this irreducible representation of the symmetric of Sn, the spec modules indexed by lambda, are given by this hook length formula, which in the literature called a miracle, because it's a product formula. This is product formula, and factorial over the product of the hook lengths So the hook length is just the boxes below and to the right of a given number of boxes below and to the right of our given square in the diagram. We go over all possible diagrams and we get the hook lengths, and we have this nice formula. But then one can take skew, a standard Young tableau, and consider, so we have the difference between two shapes lambda and mu, and what is the number of ways to assign the numbers from 1 to n in these boxes so that they're strictly increasing along rows and down columns, and only each number appears exactly once. The same notion, what is the number? Well, these are the formulas that we have for these numbers. From the literature, there is a determinantal formula which tells us that it's efficient to compute these numbers. But it's not a positive formula, so if you actually want to extract asymptotics from here, it's going to be quite hard. There is the Littlewood-Richardson rule, which is a positive formula, but then the Littlewood-Richardson numbers themselves are hard to compute, so it's also not very useful. And on the other hand, we cannot expect anything nice because we have this type of numbers, the Euler numbers, which have this transcendental generating functions appearing, are also a special case of this skew standard Young tableau, so we cannot really hope for a nice formula. And what was recently discovered, and it came from the study of Schubert calculus, was this type of formula for the number of skew standard Young tableau, the given shape, and it is a very compact sum over products of hook lengths, just like what I showed you earlier, and has nothing to do with the previous formula. So what are these excited diagrams? They are all the possible ways we can move the boxes of mu inside lambda along slide them along their diagonals without passing each other. So these are all the possible excited diagrams. For each of these excited diagrams, we take the product of the hooks of the boxes that are in the diagram. We get this sum over all possible configurations, and we get the number of skew standard Young tableau. And then there are generalizations. You can put powers of q and so on, so I'm not going to go into these details. But the way this is proven is quite interesting. So one does the localization formula for the Schubert class of the Grassmannian, which are indexed by permutations, and this gives this formula, and this there are these determinants, and this is the end. This is where the determinants came from. Basically, these excited Young diagrams correspond to Lozenge Tilings. This type of evaluation of the Schubert class corresponds to these weights that I said, and then the other side of the story is that the Factorial Schur functions, which are also these Schubert classes in this case, have determinantal formulas.